All right, this week's topic is the Milky Way galaxy. I don't know how many of you have been able to observe the Milky Way, uh, but it, for me, is one of the most incredible things that you can see in the night sky. And the picture that we have here in the opening slide is what you would see if you took a time lapse photograph with really nice equipment. So, this is an all sky view, and you can see that there's a swath of light that passes across the center of the sky. That is the Milky Way. But then you also might see these other fuzzy patches here. Those are the large and small Magellanic Clouds, two other galaxies that we can see in our night sky. And I'm not sure, but I think this might be the Andromeda Galaxy. And so most every dot in this picture is a star, except for the few galaxies that I pointed out. And all of these stars are part of our Milky Way galaxy. Okay, so how would you see the Milky Way? Uh, find a very dark place, find a clear, moonless night, and look directly overhead. So I think the best way to do this, I know some of you are probably still working on your moon and stars observation lab assignment. Uh, so obviously one of those you're supposed to go out and find the moon. But if you're not specifically looking at the moon, it's nice to observe when the moon is not around. And if you go out on a moonless night, look up in the sky, find a very, very dark place to look, like the darkest part of the sky that you can see, and stare at it for a few seconds. And the reason to do that is to help your eyes adjust to the darkness. As your eyes sort of focus on that dark spot, anything bright around it is going to come into slightly better focus. And those faint spots of light from stars will appear a little bit brighter and sharper in image. And once your eyes have adjusted, if you have a nice clear moonless night, you might all of a sudden look overhead and see the Milky Way appear in front of you. Now, the picture that we have on the screen right now is obviously another time-lapse image. It's not going to look this clear, but it will look maybe a little more clear than you might think. And I know the first time I observed the Milky Way, I was sort of surprised that I'd never seen it before. I felt like, how have I never really seen this before? It's such a stark and large feature that spreads across the whole sky. It like cuts the sky right in half. But it's a matter of going out when it's clear, no moon, and letting your eyes adjust to the darkness, and then the details of the Milky Way will start to appear for you. You'll see the bright and dark features. Now, the Milky Way itself is a pretty incredible object in the universe. It is about 250 billion stars, and it's about 100 million light years across. So remember, a light year is the is the distance it takes light to travel in 1 year, 100 million light years across. So when we look across, if we could look across to the other side of the galaxy from end to end, the stars that we would be seeing there, the light from those stars would be 100 million years old. So it's hard to fathom this, but 100 million light years across and 250 billion stars within the Milky Way. So that's what we're trying to wrap our minds around in the lecture today. Now, the Milky Way has been known of for a long time. Back before the days of light pollution that we're in, the Milky Way was a little bit more obvious to people. And so the Milky Way itself has been known about for ages. However, what it was and how it's composed and where we are within it, all of that information has been sorted out in the last couple hundred years. Now, if you go back to 1785, William and Caroline Herschel tried to map out the stars in the Milky Way and figure out where we were in it. Now, they did have a limitation, and that's that they could only really see the stars that were within about 6,000 light years. Let me pause for a second. Remember, the Milky Way is, we know now, 100 million light years across. So they could really only see a small sample of all the stars in the galaxy, only 6,000 light year radius around us. Now, what they concluded based on that is that there seemed to be about the same number of stars in every direction in the sky, and so we must be relatively close to the center of the galaxy. That is kind of the default. Think back through history, right? We're on the Earth. The default is, well, probably everything is moving around us, and so we're probably at the center of the universe. That was the geocentric perspective. Then our observational data got better, and we realized, well, that's not exactly right. We're not at the center. We're kind of offset. The center is the sun, and that became the heliocentric perspective, that everything is going around the sun. Well, now in 1785, this, I don't want to say mistake, but this default position is happening again, where all around us it seems like space is organized in the same way. There's about the same number of things in every direction, and so it makes sense that we would be in the center of the galaxy. Okay. Now, they weren't quite right about that, but they did get the general shape of the galaxy right, that is sort of flat and spread out. Now, again, this 6,000 light year window made it seem like the galaxy is much thicker relative to its width than it really is. And we'll see in the coming slides just how narrow, how thin the disk of the galaxy is. But the overall shape is correct. The galaxy is spread out like a disk, almost like the solar system is spread out like a disk, and pretty much for the same reason. Now, as I've been saying all along, or since we've studied light, everything we learn in astronomy is by dissecting the light that we can take in. And so we need to take advantage of all of the different bands of the electromagnetic spectrum. And for doing galactic astronomy, for studying our own galaxy and then later for studying other galaxies, visible light is great, but it's very limited because visible light gets absorbed or blocked by dust. And it turns out there is a lot of dust in the disk of a galaxy where we are. We're in the disk of a galaxy, and so to see the rest of the galaxy, we have to look through a tremendous amount of dust. Now, fortunately, longer wavelengths of light penetrate through dust very easily, or much more easily. And so if we use an infrared telescope, we can actually see the galaxy much more clearly. So compare the two images on the screen. Visible light on the top, infrared light on the bottom. Infrared light is way brighter because that light is coming to us much more easily through the dust. Now, you can still see evidence of dust. There's like some places that the light is getting blocked, but it's not nearly to the same extent as visible light. It's like the difference between like a totally cloudy day and a slightly partly cloudy day. So we can learn a lot more about what's going on deep into the galaxy by looking in infrared light and radio waves. Long wavelength light can help us learn about things that are far away, where there may be dust and gas in the way, because the infrared light and the radio waves, long wavelengths, don't get absorbed as easily or very much at all. And the last point on this is, if we could see infrared, just imagine how different our perspective would be on the night sky. The fact that we can see visible light means a lot of the galaxy gets obscured, and so only really the stars that are very close to us show up as bright dots in the sky. And so we have like the star Sirius is, unless there's a planet available or the moon's available, the star Sirius is the brightest star in our night sky right now. Well, if we could see infrared, the brightest thing in the night sky all the time would be the galactic center. And so I've often thought about this. I wonder how that would have changed the science of astronomy. Like when we have figured things out, because our perspective on the night sky would have been totally different. Rather than thinking about things in terms of the local neighborhood of the Earth and the sun, because those are the stars that stand out, we would have had this really one big dominant thing in the night sky. And so past scientists, astronomers would have had to come up with theories about why that's there and what it means and what it represents and how far away it is. And so I wonder, how that would have changed things. But that's not the view we get. The view we get is this one, this visible light image. So we've been talking about the Milky Way specifically, just a brief detour here to survey the other types of galaxies. And we will be talking more about galaxies in general next week. But for now, there are three types of galaxy. There's the spiral galaxies, there's elliptical, and irregulars. And really there's like two kinds, the spiral and the elliptical, and then the third category is anything else that doesn't fit into a spiral or elliptical shape, we throw into the irregular category. The spiral are probably the more familiar. I imagine if you think of a galaxy, those of you who have kind of a conception of a galaxy in your mind's eye, is probably the spiral shape. But there's a fair number of galaxies that are also elliptical shaped, where they're more round and you can't see any spiral structure to them. Now, within the spiral category, there are two subtypes. There are unbarred spirals, which are the ones on the top, on the right-hand side on the top. So over here, these are unbarred spirals, and then we have barred spirals. And they're called barred spirals because it looks like there might be like a bar running through them. And so it's not totally circular and symmetric. It's sort of been stretched out a little bit in this direction. Okay, so the spirals come in two subtypes, and then there are ellipticals and there are irregulars. There are other subcategory classifications of these, but this will be enough for our purposes to distinguish the galaxies in these 3/4 categories. So which type is the Milky Way? The Milky Way is a barred spiral galaxy. It's not perfectly circular. Now, let me just pause for a second here. This is a diagram of the Milky Way. I've shown you pictures of our Milky Way from our perspective. We can't really go outside, or we have never had the capability to go outside of our own galaxy and take a picture of it. So all of this information that I'm telling you, we've had to infer from our position within the galaxy. And that's kind of an impressive thing if you think about it. Not only have we gone to figure out that we have spiral arms, but much more specifically, we have spiral arms around a barred spiral center. And so that's the level of detail that we've been able to make measurements of the Milky Way galaxy. There's a central bar here, so it's not completely round. It's kind of stretched out in this dimension. And around that central bar is what we call a nuclear bulge. So here's the side view of the galaxy. It's a little bit thicker around that center portion, but the galaxy is very, very thinly stretched out. So it's showing you in the diagram where the sun is, 26,000 light years from the center. Now remember that I said the whole galaxy is about 100,000. I think I put 100 million. I think it should be 100,000 light years from end to end. I'll have to fix that. It should be 100,000 light years from end to end. And so the sun is like halfway. from the center of the galaxy to the edge. So it's about halfway from the center to the edge. That's where the sun is located. But if you compare this dimension to the thickness of the galaxy, it's only about 400 light years in the thinnest part of the disk, and then there's kind of a fuzzier region that extends about 2,000 light years. But 2,000 compared to 26,000 means that the galactic disk is relatively thin, right? Compared to how much it's stretched out this way. It's fairly thin from side to side. Now, surrounding, if you go outside of the disk, there are these globular clusters that exist outside of the galaxy. They're still part of the galaxy, but they're outside of the main disk. All right, we're going to take another look at a map of the Milky Way. So here is a map that has been centered on the sun, and so you can see where we are. The sun is in a region called the Orion Spur, and it's just adjacent to this large Perseus arm, right? So there's two really large arms of the Milky Way. There's this Perseus arm, and then there's this other Scutum Centaurus arm. Those are the two largest ones. And then there's these smaller armed features within as well. And we're kind of in between here at this Orion Spur. Now on the diagram over here, we zoom in on the Orion Spur. It's called the Orion Spur. We call it the Orion Spur because it's where the Orion Nebula is located. All right, so the Orion, and this line here is for the sun. So the Orion Nebula, which if you go out and find the constellation Orion, look at the three stars of the belt, the one on the left, go just down below that star, and you'll see a little fuzzy patch in the sky. That's the Orion Nebula. And in terms of the galactic scale, it's pretty close to us in space. And so we can get a pretty good look at the Orion Nebula. It's one of the neatest things to see either with binoculars or with a small telescope. So since we're a spiral galaxy, it'd be nice to have a little sense of how spiral arms develop. And it turns out that they are a naturally occurring phenomenon that is at least partially due to the way clouds of dust and gas will orbit around one another. Something called differential rotation will happen, which means that it's rotating a little bit faster inside than outside. So this simulation shows two clouds of dust and gases that have come close enough to where their gravity starts to influence one another, and so they end up in an orbit. The nearer parts tend to orbit around a little bit faster, and so what happens is the tails get left behind a little bit, and if you keep fast forwarding, those tails stretch out and turn into spirals. But if you kept fast forwarding from this, these spirals would get tighter and tighter and tighter bound, and so eventually the spiral structure would get so subdivided that it would basically be indetectable, right? The detail of the spiral arms would fade away because it's been swirled around itself so much. It would just basically look like a big circle. And so that's been a puzzle for astronomers to figure out how exactly galaxies are evolving. And it turns out that at the early stages, there's actually a lot of turbulence happening in the galaxies, in the dust and gas of the galaxies. And that sort of slows down this evolutionary process. And when you factor in the turbulent motion with the rotation, it takes a little while for things to settle down, and they ultimately end up in an equilibrium. Now, if you ask me how we know this, there's really two things. One is we can look across the universe to find galaxies that are in different stages of their evolution. Just like we could do for individual stars, see a star that's just been born of one temperature and compare it to a star that's just been born of another temperature. And then look at stars that are billions of years older or 100 millions of years older. And by looking at, because there's so many stars available in the universe, we can map out the life cycle of a star. Similarly, we can do that for galaxies. And so we get a lot of information from that. And then the other thing we can do is use our knowledge of physics and build that into computer models and see what happens when you just apply the laws of physics to two clouds of dust and gas that are in contact with one another with heavy amounts of turbulence. And the models are able to reproduce what we see out in the universe. And so we have a reasonably good understanding now of how galaxies come to be the shape that they are. All right, one more look at the diagram of the galaxy. Here's where the sun is located. We've got the bulge at the galactic center. This outer bubble where the globular clusters are located is called the stellar halo. I don't know if I've used that term yet, but it's called the stellar halo of the galaxy. And then we can distinguish the thin disk from the thick disk. And this table gives you some quantitative information comparing the different regions of the galaxy, the thin to thick to stellar halo. I just want to draw our attention to a couple of things. One is that the majority of the mass is located in that thin disk, and that's why when we look up in the sky, that's the brightest part of the Milky Way, is that disk right at the center. And so it's also the brightest, but then also it's the youngest. It gets older as you move from the center, from the thin disk to the thick disk to the halo. So the halo is the oldest part of the galaxy. And those globular clusters are the older stars in the galaxy. Okay, so we've seen the diagram showing the formation of the spiral arms. Just want to say a little bit briefly about how the galaxy becomes the general shape it is, not just the spiral arms specifically, but the general shape. And it's the same idea as if you were making a pizza and you start out with a round pizza dough and you spin that round pizza dough around. I don't know if any of you can have done this or seen people do it, where you throw the pizza dough up in the air and spin it around, and there's a reason for that. That helps to stretch the dough out and flatten it out into the shape of a pizza. The exact same thing will happen with a galaxy. It starts out as a big cloud. As the material falls in, it will tend to spin faster, and as it spins faster, some material will get left behind, other material will get pulled in and flattened out. And so this process here is showing that flattening. There tends to be still a little bit of a bulge left in the center, some left behind globular clusters out here, and these tend to be things, so as the galaxy was forming, these things formed first, right? These stars formed first, so as material was falling in, they were able to concentrate some things that did not get pulled into the main disk of the galaxy, which sort of explains why the globular clusters would be older than the material in the disk. The non-star, the material that has not yet formed into stars would be a little bit more diffuse and easier to pull and stretch and fall into the disk as it's spinning. And as it spins out, eventually those stars will turn on, and sort of like turning on the lights. And so the lights would have come on the outside with the globular clusters, and then from the disk to the center get brighter and brighter, and eventually it reaches an equilibrium. And this certain shape where it's skinny, little bulge, but long end to end with a collection of globular clusters in the halo. All All right, this is a slight aside, but we're going to get right back to the Milky Way in the next slide. What we've plotted here are the planets. On the x-axis, we have their distance from the sun, and on their y-axis, we have their orbital speed, how fast they're traveling. And the line shows what the theory of gravity predicts, and it all works nicely. That as you go farther from the sun, their orbital speed goes down. So this is something we've already covered. We've talked about it, and hopefully it all makes sense to you why that would be. When gravity is weaker, there's less pull, or given last week's lecture, space is less curved. So that means that they're not going to be accelerated as much. And the things closer to the sun, gravity is more curved, pull of gravity is stronger, and they're accelerated faster. Okay, so this is pretty a sensible thing. And so what we expect in the solar system is exactly what we see, that as you go away from the sun, things start to slow down. So, given what we know about the structure of the galaxy, we would expect a similar thing to happen there. That as you move away from the center of the galaxy, eventually you'd reach a point where most of the matter is heading towards the center and not sort of behind you, and the speed should start to fall off and get smaller and smaller as you get further away from the center of the galaxy, just like they do for the center of the solar system. But that is not what we find. So this is another rotation curve. This is the galactic rotation curve. And there's some bumps and wiggles. You might be able to guess why that is, right? So it's a little bit more complicated than the solar system because you don't just have one thing at the center. You do have a concentration of material at the center of the galaxy, but then it's sort of spread out. So if you're a single star moving, and you're thinking about moving away from the center of the galaxy, you're not just moving away from one object, you're moving away from a collection of objects and also into slightly more spread out objects. And so the bumps and wiggles here are indicative of the spiral arms, right? So as you're going from zero, there at first is an increase in the orbital velocity because you're sort of getting out from the central region of the star, where the further you go back, the more material is sort of within your orbit. And then you get outside of the center and it starts to drop off, just like the theory of gravity would expect. But then you pass into the next spiral arm and it goes up again. Then you pass out of the next spiral arm and it starts to drop like gravity would expect, into the next one. But eventually, you'd always expect that you'd get to a point where it's just going to decrease from here on out. And this blue line is indicating what gravity predicts should happen with the Milky Way galaxy. So all these bumps and wiggles are fine, but then eventually it should just drop off like the previous graph, because you're not passing through any more arms, and these stars out here should just get slower and slower and slower. But what we see is the red line, and it actually, you could either say it flattens, but it's sort of like it's still even increasing. And so these stars out here are actually orbiting faster than the stars that are just outside of the core. It's as if Neptune was moving faster than Mercury. It doesn't make any sense. In fact, the only way to explain it is if there's matter out there that we can't see. And this was an observation that Vera Rubin made, and it's become known as dark matter. I don't believe she coined the term, but she's sort of the scientist who figured out the problem. And I think dark matter was a term that came before her and then it got applied to this stuff. It's not necessarily a bad term. It can be a little bit misleading. It's not just dark. It's completely invisible. and it's invisible in every wavelength of light. We can't see it in X-rays. We can't see it in radio waves. We can't see it in anything in between. It does not apparently interact with light in any way, but we think it has to be there because the only way for these things to be getting pulled at these speeds is if space was really curved in that area, or there's some gravity that's pulling on it. And that's the theory of dark matter, that there's material out there surrounding the galaxy, accelerating, curving the space at the outer edges of the galaxy, but it's stuff that just cannot be seen in any way. It's weird. One more thing on this, how much of it? So if there's a little bit of weird stuff, you're like, well, we can deal with that. But in this case, the weird stuff, it turns out, has to make up 95% of the matter of the Milky Way. So it's not just a small thing. You can see from the graph that it's a pretty big difference. But it's not just a small amount of matter that could be causing this. It has to consume 95% of the matter of the entire Milky Way. So we really don't understand 95% of what's happening in the Milky Way. Or in a sense, we don't understand 95% of what's happening. Only 5% of the galaxy is made up of stuff we even have a theory to explain. But it is not just the Milky Way that is weird in this strange way. In fact, when we look at other galactic rotation curves, they all do the same thing. Now, we don't have the same level of detail in them, so we don't see, like, in all of them anyway, the sharp bumps and wiggles in the curve, but they all do this general thing where the curve flattens out. Instead of dropping off, instead of coming up to a peak and then dropping off like we expect them all to, they flatten out. They all have the same shape. And when we check it out with how much dark matter must be there, for all of them it's about the same. It's 95% dark matter. So not just the Milky Way is 95% dark matter, but all galaxies are apparently 95% dark matter. There are some theories about what it is and what it could be. You're welcome to go read about those things on your own. There's not really any strong scientific evidence that points in one particular direction. The only thing I can tell you about them with any certainty is that the dark matter does not interact with light in any range of the electromagnetic spectrum. And given what I've said, that everything we can learn about astronomy is by studying the light that we can collect, means we haven't really been able to study dark matter very well. Now, there are ways to make inferences about it, but you kind of have to stay tuned on that one. It's a subject of a lot of active research, and we don't have any solid answers right now. Okay, so let's go so the dark matter is on the outside part of the galaxy. Let's go into the center. Let's look into the center of the galaxy. And I'm going to introduce this, and then I've linked to a video by Andrea Gatz, who is an expert in this area, and I encourage you to watch her talk where she explains the observations her team has made and what they've seen by studying the center of the galaxy. But if you're just out in the night sky and you want to point to the center of the galaxy, what you have to do is find the constellation Sagittarius. Okay, so this is a look at Sagittarius in Stellarium. So you can start there, open Stellarium, search for Sagittarius, and it will show you this image. It might not show Saturn there. I might have taken this screenshot a year or two ago, so Saturn has probably drifted off to move past Sagittarius and into another constellation. But you can recognize Sagittarius by identifying the triangle and it sort of to me looks like a teapot with a handle, but I'll let you decide what you think it looks like. But if you can identify the triangle shape, then that triangle leads to the tip of the arrow. Now let me go over here to the right. This is a high definition image of the night sky with the center of the galaxy. So you've got the triangle that leads into the arrow. The arrow doesn't exactly point to it, but it kind of points in the general direction of this place over here. That's the galactic center. The thing that's here at the exact galactic center is called Sagittarius A star, and as you'll hear about in the video, it is a supermassive black hole. It's what we call a supermassive black hole. That is a technical term. It's very different from the black holes we studied last week in that instead of being created from a single star that's gone through its life cycle, this is the masses of hundreds and millions of stars. And so maybe they're similar in some ways, but there may be some differences with their structure and function. Okay. Here are a couple of different views, or 3 different views: infrared, X-ray, and radio. So you can see what's happening at the center. Let me click back to the previous slide. The exact point where the galactic center is, you'll notice, is pretty dark. And that's because when you're looking at the galactic center, you're looking exactly through the disk of the galaxy, and so you're looking through a tremendous amount of dust. So we don't see the galactic center as a bright spot in our sky. Where the Milky Way is bright in our sky, in visible light, is just outside the disk, so we're sort of looking through less dust. But where the galactic center is, there's a lot of dust. So if we take our highest powered telescopes, we can focus in, and even looking at X-ray with very sensitive technology, looking X-ray vision at the center of the galaxy, and see that there are individual stars orbiting around this center. And so this map here is showing the orbits of those stars. By studying, and I'm getting into a little bit of what gets explained in the video, by studying these orbits, they can infer how much mass must be concentrated at the center, which I think is somewhere around here. And by confining the size and this amount of mass, they were able to determine that the only way for that thing to have that much mass in that small area is if it is a black hole. And because of the amount of mass, we call it a supermassive black hole. And so this is infrared, X-ray, where we can track the motions of individual planets, and then in radio waves, where it's sort of its brightest, because that light gets through the dust and gas most easily. So here's Sagittarius A star, or the supermassive black hole at the center of the galaxy. Okay, now in the video by Andrea Getz, you'll see a discussion of this image here, where they use some really creative technologies to clear up the image and actually be able to resolve individual stars at the center of the black hole. Remember, that's 26,000 light years away from us. And so it's some pretty cool technology, and there are some interesting things. I also linked to another article with a short video in Quantum Magazine, and I'd recommend that you both watch this video and also take a read through that article to learn more about the supermassive black hole at the center of the galaxy. Okay, now before we leave the Milky Way, I wanted to mention our nearest large neighbor is the Andromeda Galaxy. And I think on the first slide I mentioned that I thought this one little blurry spot was the Andromeda Galaxy. You can find the Andromeda Galaxy with a telescope. I don't know how many of you have access to one, uh, but you can find it. It will be blurry. You won't be able to see very much detail, but you'll be able to see this general shape in the sky, right? So it'll be easily distinguished from what a star looks like, or what a planet looks like, or even what a nebula looks like. And it is significantly larger than the Milky Way. The Milky Way is 250 billion. Andromeda Galaxy is about 4 times larger. It's 1 trillion stars in the Andromeda Galaxy. And if we fast forward many years into the future, I decided to put this whole figure in from the textbook. Fast forward 3 billion years, our two galaxies will actually begin a process of colliding. Luckily, 3 billion years from now, that's not going to be much of a problem for us. And this is a simulation of what that would look like as the Andromeda Galaxy enters into our night sky and collides with and really tears apart the Milky Way galaxy. And this also shows you how an irregular galaxy can be formed. So how does a galaxy go from being either a nice spiral or elliptical, symmetric looking shape to something irregular? The answer is it probably collided with another galaxy. And so look at the pictures here. We have a spiral galaxy, and then our Milky Way is a spiral galaxy. They're colliding. As they're colliding, they have this strange, you can see some structure in it, but it's obviously deformed shape. So this would be, if we saw a galaxy that looked like this in the sky, we'd say, oh, that's an irregular galaxy. And it's still an irregular galaxy, and it's another irregular galaxy. And then eventually, as the galaxies settle down, they end up in a big elliptical galaxy. And so that's where we're headed. So this figure caption takes you through the process. It begins in about 3 billion years, and then settles down eventually in about 7 billion years into this. Just thought I'd end there with that neat little fact about our two neighboring galaxies, the Andromeda and the Milky Way.